Hello there. Oh my goodness, I think the sound is a little too loud. We'll bring that down a little bit. Welcome, welcome. Want to be quiet, but not too quiet. I hear an echo. Let me take care of that. Working on it. All right, I think I fixed it. All right, how are you? Who's here with me so far? I'll give a little bit of time for you to come in. But I do want to get my Lofi going. And I'm curious if you can hear the music or not. So, if you are here, let me know. I'm just going to get this stuff set up. Okay, perfect. Welcome, welcome. I'm not used to having music, so I really want to make sure it's a good volume. I think it's okay if it's not too loud. Too loud is worse than not loud enough, in my opinion, so do let me know. And I'm gonna give you a little preview of what I'll be talking about, what it will be working through today. Bring your homework, or you know what else you can do? Is you can just do homework. And this can be in the background. And if any questions do arise, then you can bring them in. So this could be just kind of a study session for us. And what I brought are a few things. So usually I work with on my ASMR YouTube channel, which, by the way, I could even put that into the chat and let you know a little bit more about that. So I have a YouTube channel that is called ASMR Chemistry. Not too shocking, right? And I've been doing that for a couple of years and really helped a lot of people, which is awesome. And I even got a few messages today where someone was saying, "Hey, Gerald 13SS." One person said it was a godsend. They were working on some chemistry problems, and it just so happened what I was teaching about in my latest video was exactly what they were studying. And someone else who's going back to college after 20 years, and they're taking chemistry. And they said they also love ASMR, so it works out perfectly for them. So that's awesome too. And this is awesome because here at this study session, live chemistry help. So if you've got any questions, don't hesitate to bring them in. Even if it's not related to what I'm going to be working through. So as you can see, I've got a molecular model kit here ready to roll. And we're going to be constructing some molecules. We will also be doing some Lewis dot structures. Those two things go hand in hand. So, oh, Eileen, that's so great. You just started your first college chemistry course. That is amazing. Well, that is my specialty, is teaching college chemistry and teaching people in their very first course as well. I usually teach that every single year. So that's great. I look forward to having you and hearing about your successes. Janice Landrade, hello. Good day to you. Thank you for being here. And I love the Neil waving his hand. And I did want to remind everyone that if you'd like to see Neil the chemistry corgi, you can redeem 500 moles, or in other words, 500 channel points. And I'll bring Neil over here. So just as a reminder that you can do that. Oh, so good to see all of you. So yeah, last week, I did, oh my gosh, what's it called? Stardew Valley for the first time ever in my entire life. It was so much fun. It was a co-stream with Victorion, and it was a blast. I really enjoyed it. So the plan is that we will be doing a co-stream again in 2 days from now. So if you check back then, we'll be doing that. But today, as the title of the stream is that it will be chemistry homework help, and we've got Lofi in the background, and I'll be doing this in my ASMR chemistry style, just like I do on my YouTube channel. So I have a question. Now I've got a few of you on here. I am curious if you hear the music in the background or not. So let me know, because I'm trying music for the first time today. And I wanted to make sure it's either there or no music. Okay. Okay, that's good to know. All right, I'll check into that. Interesting. Okay, I might try and just see what's up with that a little bit later. Moncads, hello. You have a nice day too. Thanks for being here. It's nice to see you. I love seeing all these familiar faces. Very cool. I think so. I can hear the music that I'm playing, and I'm just guessing that the mic isn't picking it up. So I just wasn't sure if it was going through the system, making its way to you or not. So I think it'd be nice if we had a little bit of background music, but I'll get that rolling. Okay. All right. thank you for that, the feedback. So 2 of you are saying you don't hear the music. So, okay. Yep. So I'll, I might try just one thing and just see. And that's okay if it doesn't work right now. I'm going to try and see if, oh, that's the mic. No, I don't want that. Okay. All right. Okay. Yeah, sorry. I was focusing. I was trying to get the music to go, and I couldn't figure out what was going on for a second, so I paused. That's okay though. I'm gonna just keep rolling. It's okay without music. So thank you. Thank you for checking in. All right, cool. So this is the plan. We have some molecules to make. And always, when you're starting out with creating these molecules and understanding what their 3-dimensional structure is, like I'm showing here, you've got to know what are the atoms and what are the bonds and where are the electrons around the central atom. That is absolutely crucial. First step. Yeah. FK12, hello. Good to see you. I love all of these familiar faces or familiar names, I guess. So Gerald13SS and Ailiu and Janice Landrade and Moncads, FK12. So cool. All right. So with this, okay, one of the first things that we learn in chemistry is what is the formula for a particular molecule that we have. And the formula is just simply those elements that are in that molecule. And we're going to be focusing on molecules. So I'm going to zoom in a little bit here so we can get in close. And the first molecule example that I want to give is ammonia. Okay. So ammonia is, I'll get my hand out of the way here. Ammonia is NH3. So this gives us a little bit of information about that we have a nitrogen and 3 hydrogens. Okay, what this does not tell us is where are the bonds? What is the shape of this molecule? That information we don't see here with the formula. But we can figure out all of that stuff based on the formula itself, and if we have handy, which I always do, a periodic table. Okay, so there is a plethora of information with the periodic table. And so then our first job is to figure out how is this molecule bonded together and where are those electrons. Okay, so, and I'm going to pause for a second and remind you of a few things that are popping up in the chat. One is that I partnered with Study Soup. Study Soup is this awesome company that helps college students in so many ways. And they have a Discord channel that is all about these resources for students. So there is a link there if you wanted to join that. And also, if you follow this channel, you are going to be supporting chemistry students, me as well, and supporting me supporting chemistry students. So it is a win-win-win-win-win all around. Okay, so let's get back to this lovely molecule, this NH3, this ammonia. Looking at this right now, you can determine where are those electrons and how is this bonded together. And so the way you would do this, starting out, is acknowledging that ammonia, NH3, it's got a nitrogen, okay? And our nitrogen has to be the central atom. That is always our first job, is to figure out what is the central atom. So let me write that here. What is... And so how do you decide that? This is always one of your first questions in figuring out what's the structure of a molecule. But to answer this, you usually need to look at two things. And one is, it must be the non-hydrogen atom. Okay, in this particular example, we've got just two types of elements. We've got a nitrogen and hydrogen. The nitrogen has to be the central atom because hydrogens can only ever have one bond. Oh, Eileen, is this a little bit ahead? This will be a lovely preview. So I'm curious what kinds of things you're studying right now. Any of you that are in your first term or first semester of chemistry, you could be, I'm imagining, talking about dimensional analysis or balancing chemical reactions or learning what a mole is, what mole ratios are. Chemical versus dimensional analysis. Ah, yes. Yes. And naming, for sure. Yeah, what's funny about this example is if you were to name it using the rules of naming covalent compounds, you would say nitrogen trihydride, but because ammonia is so common, it's kind of like water. So it's just got its own name and nobody calls it nitrogen trihydride. But we did maybe 2 weeks ago, I think, on a live stream, we did some naming, and we can definitely do more naming at any point. So, Eileen, you, oh good. If there is a particular kind of problem you want to do, it could be naming, or I've got my calculator handy, so we could also do dimensional analysis. I am totally open to anything. So let's look at this ammonia for a second, and then do let me know if you have a question, and we'll go through any of the examples that you might have. That'd be great. Okay. So choosing a central atom, it's got to be a non-hydrogen. Also, it is the least electronegative. Atom. All right. The least electronegative. So electronegativity is the ability for an element within a bond to pull electron density towards itself. So fluorine is the most electronegative. Oxygen is the second most electronegative. And so our central atoms tend to be less electronegative, because that then allows the external atoms on the outside of the molecule to essentially hog all the electron density for themselves. So, oxyanions. Yes. Yeah, the oxyanions are really annoying. But I do have a little trick that might help. I'll share that in a minute. I found it helpful for me. So let's draw the Lewis dot structure for ammonia, and then I can talk about that. So what we want to do here is the Lewis dot structure. A Lewis dot structure is not the three-dimensional structure, but instead it shows bonds. So what is bonded to what? In other words, what elements are next to each other and sharing electrons? So this would be where they are. And then it also shows us whether those bonds are single, double, or triple bonds. Okay. That is essentially each bond. This would be one pair of electrons is a single bond. So then that means two pairs. Okay, so you get the idea here. Three pairs. All right, so we can understand better not only where the bonds are, how strong they are, and it also shows if there are any lone pairs. Oh, I'm about to run into that. Separate that out. Okay. Shows lone pairs. And then from the Lewis dot structure, we can figure out the three-dimensional structure. But having a correct Lewis dot structure to begin with is absolutely imperative. So it is something that is really important to get to understand and be able to do. So going back to ammonia, we identify that central atom. And so we say, well, there's really only one choice. It's got to be that nitrogen, because those hydrogens are the other elements that are there. So nitrogen is in the center. And what you get to do then is you surround the central atom with the remaining elements. And you know that if it's part of the molecule, that there must be at least one bond to them, or else if they're not bonded, they're not part of the molecule. So right off the bat, you can bond all three of those hydrogens to the nitrogen. The hydrogens have to be directly bonded to the central atom. It can't be, here I'll show you what it's not. You can't say this. Okay, because this implies that this hydrogen has two bonds, one there and one there, and that is impossible. Hydrogen can only ever have one bond. It is too small to be able to have more than one bond. It can only have 2 electrons maximum, and that's just one bond. So this is not going to happen. So I can do my big no. Not gonna happen. Okay. So right away then, we can identify that we have somewhat of a skeleton structure here. Right now, what I've drawn is not necessarily the final Lewis dot structure, because we have not counted up the electrons yet to see whether they're all there. All right, so what I mean by that is the Lewis dot structures, they include all of the valence electrons. And if we count up the valence electrons, those are in the outermost shell. And yes, Ailey, this is probably ahead of where you are. So here, I'm going to move this up. But as a preview, the number of valence electrons you can count by using the periodic table. So first, let's just find that nitrogen. Here's nitrogen. Okay. It is element 7. So a nitrogen atom has 7 electrons. But here's the question. How many electrons are in the outermost shell? Well, that is how many are in this row, this period. If you count across, starting with lithium, beryllium, boron, carbon, nitrogen, that is 1, 2, 3, 4, 5. That is the number of valence electrons for nitrogen. Okay. The remaining 2 are in period 1, and those are the core electrons. Those electrons are too deep in the atom to participate in bonding and sharing with other elements. All right, so it's only those outer electrons. Oops. Okay. So what we just discovered is nitrogen has 1, 2, 3, 4, 5 valence electrons. And so we can go back to here and say, all right, nitrogen has 5 valence electrons. If this is our tally that we're doing. And then the 3 hydrogens that we have, there are 3 of them. And each one of them has 1. So that's a total of 3 electrons that are contributed to the molecule by all 3 of those hydrogens. Nitrogen, there's just one nitrogen. So let's put 1 times 5 equals 5. Add all these up and you get 8. 8. What does this number mean? Okay, this is 8 electrons. This is the total number of electrons that are being used for bonding this molecule together and that are in the outermost shells. Okay, so what that means is when you add these up for a molecule is the number that you see here has to equal the number of electrons that are represented in bonds or lone pairs in the Lewis dot structure. So this needs to be consistent with what we see here. Okay, this line, this is a single bond. Single bond, that is one pair of electrons. So right in here, what this means is that there are 2 electrons that are being shared between nitrogen and hydrogen to create that bond. So that's 2 electrons. Here's another bond. 2 electrons. So that's a total of 4. Over here, 2 electrons, total of 6. So this structure we have drawn so far is showing 6 electrons. That nitrogen only has 6 electrons, and the molecule only has 6 electrons. But adding up all the valence electrons, there should be 8. That means we are missing 2 that we need to account for. We've used all the electrons for bonding. That means that there's a pair of electrons that are on the nitrogen. That pair can't go on the hydrogens. They're already maxed out. They've got their 2 that they're sharing here. This one has its 2 that's sharing. 2 that's sharing. Nitrogen, though, to have its octet, following the octet rule, atoms are most stable with 8. It's got its octet, if we have 2 there, that then is now consistent with the number of electrons there needs to be in this molecule, and it satisfies the octet rule for nitrogen. So ultimately, I'll bring my green pen now. This is the Lewis dot structure of ammonia. And all those explanations, all of that, this is one of the most effective and reliable ways to draw your Lewis dot structure. And I say it's one of the most reliable ways because what I have seen is this. This does not work all the time. That some people learn, maybe I'll use my purple, I'll get out my purple pen. Some people do it this way. They recognize that nitrogen's in the center. They recognize that nitrogen has 5 electrons. And so then they start drawing their dots. And if they're thinking ahead, they're thinking, okay, here's an electron, there's an electron, here's an electron, but I need to make a bond with hydrogen there, and then I'll put another electron there to share with the other hydrogen. And then they'll draw their hydrogens around, and each one of these hydrogens, you could say, oh, it's contributing an electron, So draw that with a different color. And then this one. And this one. Each of those has one. Okay. And then here is a Lewis dot structure of ammonia. Here we show it with dots. Here we show it with a line. Those are just two conventions to show the same thing. A line here shows a single bond, which is a pair of electrons. Showing these two dots, that's a pair of electrons. Okay. And here we're kind of designating these two electrons are purple, they belong to the nitrogen. That one's purple, it's the nitrogen. This one's red, it's the hydrogen. And this worked just fine for this example that we gave. Unfortunately, doing it this way does not always work. And so that's why I always have my students tally up the total number, decide which one is in the center, and distribute them around. Doing it this method, you don't fall into problems that you can in other ways. So, this one's kind of cute though, I gotta say. Especially if you have colored pens. So, all right, so there's a little example of our Lewis dot structures. I wanted to show you my trick for oxy acids or oxyanions. Oxyanions, that's what you said. Okay. So let me set my periodic table aside. And maybe I'll flip this over. Get a fresh sheet of paper. Okay. All right, I'm going to try something for a minute. I want to see if you can hear. I just turned up the music and I'm curious if you can hear it. Sometimes music through a mic sounds bad or weird, so I'm just curious if you can hear it or not. Okay. Oh, cool, you can hear it. Okay. Oxyanions. So, you had written in the chat, or which is the least? And were you talking about least electronegative? Because I think that's when I was doing the Lewis dot structure. So I just wasn't sure if I missed something that would have been helpful for you. So let me know if that's something we should talk about more, or if we got it covered. Gotcha. Okay, yeah. All right, let's talk for a minute about naming oxyanions. And I'm going to use a couple different examples. All right. So one of them is this one. Okay. So do any of you know what this oxoanion is called? What is the name of this? Yeah, good job. Sulfate, exactly. Okay. All right. Now I have a different one that's related but different. Okay. This is, it's still sulfur, oxygen, and it's -2. But instead of there being 4 oxygens, there are 3. So does anyone know what this one is called? Yeah. Well, I'm going to hopefully help you with that. That's my goal today. Yeah, sulfate. Exactly. Okay. Sulfate. All right. So this is something that helped me, and it had to do with my Spanish. Okay. So I lived in Colombia in high school and learned Spanish then. And in Spanish, there is something that you add to the end of a word to make it little. Okay? So depending on the word, you put ito at the end. Like hijo is son, and if you say mi hito, or I guess that's, yeah, if it's hijo and then hijito or mijito, my little son, or mijita, and mamacita. So this is called a diminutive, and diminutive is like a word that's endearing, and it also making something smaller. So if there is something and it's like, oh no, it's just a little one, then you add the ito at the end. Okay? So there's several languages that have the diminutive. I'm not sure if I can spell this right. Diminutive? Is that how you spell it? Okay. And so like in related to the English word diminished, making something smaller, diminutive, making it little. And it's usually little, cute, sweet, has a positive connotation usually. But the main idea here is that it's smaller, okay? So I remembered that sulfite was the one with fewer oxygens because it was ite, I-T-E, like ito. So I was like, oh, it's like sulfito. It's the little sulfate. Sulfite, fewer oxygens. All right. Now, here's another example, because it does get, there's some complexities here. So let's look at this one. Okay. This is NO3 minus. All right. So now instead of -2, it's -1. And this is a nitrogen. Okay. So does anyone know what this one is called? NO3 minus. Nitrate, indeed. This is a really common, very common oxyanion. Okay. So here's our nitrate. So following the same trend, this is sulfate and one less oxygen with sulfite. Then let's go the opposite way. And what would be the formula of nitrite. And I know you can't do subscripts in the chat. That's okay. Yes, exactly. So reduce the number of oxygens by 1. Exactly. Good job. NO2. It's the same charge. You're just removing one of the nitrogens. So again, here's nitrate, and here's the nitrite, or the nitrito. The little nitrate is nitrite. Okay, so what you do need to recognize is that your sulfate does have 4, and even though nitrate has that same ending, it does have fewer oxygens. Now, yes, the charge always does remain the same. Like the Led Zeppelin song, the song remains the same. The charge remains the same. It does. And the reason is, if you want to know the reason, I will tell you. And it all has to do, I swear, you go back to the periodic table and you can explain almost everything. And the reason why this works is by virtue of oxygen having 6 valence electrons. It's fascinating how this works, okay? And I'm going to show you. And it is tied in with the Lewis dot structure, okay? So the fact that we just did a Lewis dot structure is 100% relevant right now. So let's see why. Okay, so how about, it doesn't matter which one, we can do either one. So let's look at the sulfate, okay? So if we were to do the Lewis dot structure for sulfate, and if we did the dots, and I'll just do it quickly so that you can kind of see how this works. And by the way, for any of you who are familiar with formal charges, I'm not going to worry about formal charge right now. It works out the same either way. Okay, so let's look at this. If we added up all of the electrons that there are, and we also took into account that this is an anion, so this is -2 charged overall, okay? We have sulfur and all these oxygens, they all have their octets, okay? So everything is stable, okay? And this is the thing, is that look at oxygen. Oxygen has 6 valence electrons. So if I circle this oxygen and it's 6 valence electrons, and if we remove that oxygen along with its 6 valence electrons, we would end up with a Lewis dot structure that is still, everything's stable, all of the elements have their octets, and because we removed the atom, the oxygen atom with its 6 valence electrons, we didn't change the overall charge because because this is neutral. We didn't take away any extra electrons or add any extra electrons. So whenever you add an oxygen atom or remove an oxygen atom from an oxyanion, you don't change the charge. And it's almost like this sort of like plugs in, like you can just pop that on to this lone pair here and the octet works out. So as long as there's room to add on another oxygen, you can add it on. Okay, so with our, as we saw with the nitrate, it's the exact same idea. You add an extra oxygen, charge is still -1. Okay. Oh, I'm so glad. That makes more sense. Yeah, so this is the good thing about understanding at a little bit of a deeper level is then you don't have to rely on memorization as much. So it helps in that way. Okay. So I wanted to help you with chlorate and chlorite and those as well, because those get a little bit complicated, but it's the same kind of idea. Okay, so I'm going to start out with ClO3, and this is minus charge. Okay, ClO3 is chlorate. All right. So, following the same pattern we've seen before, what do you imagine ClO2 is? That's our chlorate. And that is chlorite. Indeed. Nicely done. All right. But this is the thing, is with chlorine, oxyanions, you have a lot more options. You can actually remove yet another oxygen and just have one left over. So now there needs to be another way to distinguish chlorite from this one. And the way that is done is by adding a prefix. And this is the prefix hypo. And hypo means low. Okay, there's a term hypoglycemic, where you have low blood sugar, is one way that hypo is used. Okay, so you add hypo to chlorite. So not only is it ite, as in ito, as in one less oxygen, but it is even more so by the hypo being there. Okay, now on the other end, up here, there is another extreme, but it's on the top end. Still, because we're just adding and subtracting oxygen atoms, all these are -1. So charge does not change, but now we have 4 chlorines. 4 oxygens around the chlorine. So now again, we need to distinguish it by putting a prefix like we did with hypo. And hypochlorite, yes. Oh, hypocrite. Oh, that is so interesting. Oh, that's a good mnemonic device. Yeah, yeah. Okay, good. So up here, the word or the prefix we might want to put here would be hyper. Okay, hyper means more, means a lot. Okay. But for some reason, the chemists who decided the names decided to not say hyper, but instead they dropped the HY and they just have per. So instead of hyper, it's just per. They drop the high. I don't know why. That rhymes. So this is perchlorate. Okay. But it does come from this prefix hyper. It's just shortened there. It looks like I put a little accent on that E. I did not mean to do that, but I kind of like it. Perchlorate instead of perchlorate. Okay. So I remember when I first learned all of these, I was really overwhelmed. But once I broke it down into what all these things mean, then it felt a little more doable. So, all right, hopefully that's helpful. All right. So far, no one has redeemed any channel points to bring Neil the chemistry corgi in, but you still could. Maybe I'll put a reminder. Oh, I'm so glad. I'm so glad that was helpful. Dextort is redeemed. All right. See, I just need to remind all of you that exists so that you can redeem all those many points that you have to bring Neil in. All right, Neil. Where is he? I think I see him. Can you see his fluffy butt? It's right over there. Oh. Neil. Neil. Hi, Neil. Do you want to come here? Hi. Hi. Come here. Come here. Oh, you know what? I have doggy treats somewhere. Where are they? Oh, look. He laid back down. Yes, he's a corgi. Neil. Neil, come on. Neil. Neil, come on. Come here. Come on. Come here. I think I need to get treats that I leave by my computer. I'm going to go get, oh my gosh, I hit that and it bounces around. I'm going to go get treats. Okay, so I'll be right back. This will just take a second. Okay, I'm back, and so is Neil. There he is. Neil, hi. Hello. Hi. A real treat. Oh, was that good? Was that good? What do you think, Neil? Sit. Let's see if he actually knows how to sit. Sit. No. Oh, should we give him another treat? Oh, he's so good. Good boy. He's so good. All right, I think he's probably gonna, I'm guessing, wander off and take another nap. Thank you, Neil. Thank you for coming into the stream. Aw. Okay. Let's see, I'm gonna turn this down a little bit. All right. What do you want about? Oh my goodness. Oh, hi Dick Stories. Oh, you said okay, so I missed oh, okay. I missed, I don't know what happened in the chat. I missed it. So hopefully, okay. I don't know, but yes, Neil. All right, cool. Well, all right. Hi, everyone who has joined recently. Hello, Dick Stories. And also thank you, Dick Stories, for bringing in Neil into the stream. All of you can do that at any point. All right. Oh, funny. Yeah, I'm not sure why. Yeah, I guess the Nightbot thought something. Yeah, I'm not sure. And hello, Liza317. Good to see you. And are you saying hi to Neil? I will tell Neil. Neil, Liza317 says hello. And he says hello. Okay, one last peek at Neil. Hi. He's being so good, like just hanging out here. Usually he goes directly back to sleep. Yeah, he's given a yawn. Neil. So nice to chill with Neil. So today, this afternoon, I was teaching a chemistry lab and he is adorable. Gerald13 says, "Oh, give a Neil wave." He is. He's very, very calm. And oh, interesting. All right. Well, I don't know Nightbot very well. So like I don't know how it works, how it decides to do what it does. But anyway, so Gerald13SS used a Neil emote. So any of you that subscribe and maybe follow, I don't know, you should try it. Those Neil emotes are available to you, so check those out. And I did want to ask you and encourage you to follow if you are enjoying it, and following helps me create more content, and it also helps chemistry students, because that is what I am here for. I am here for helping as many chemistry students succeed this year as possible. I would love it. Oh, this is my dream. If everyone's grade went up and their understanding went up and there were more inspired scientists or just people who want to understand science a little bit better this year, And if I play a little bit of a role in that, I would be so happy. So if you follow, then you're supporting this stream and you can help make that happen. So please do consider following if you haven't already. So thank you for that. Of course, you can also subscribe, which is also super awesome as well. And I wanted to thank Study Soup. Study Soup is this amazing company. They are the sponsor of this stream, and they are also all about helping and supporting college students in chemistry, but not just in chemistry. They have a lot of resources, and I mean a lot. So you can find out more on studysoup.com, but just to give you an idea, they've got, in terms of help with homework things, they have resources in that realm. They also have textbook survival guides, and as well as the things that can help you academically, they also hire students. So if you become a note taker with them, you can make money. So there's a job possibility for you as well. They also have really cool t-shirts. I'll show you. I get to wear their t-shirt. Yay! So there's Study Soup. Super cool logo, and I love the color too. It's really awesome. So Neil. There's a link to, you might notice if you wanted to join the Discord as well. So that's in there too. All right, awesome. You know what I loved about this is that I started out talking about Lewis dot structures, and I almost felt like I was switching gears to talk about oxyacids, and then it turned out to be totally relevant and explained part of it. So that's cool. And so given that, we really can go in any direction now. We could do some molecular structures. We could do more naming. Literally anything. So I'm pretty much at this point, because I've taught chemistry for 22 years, I can pull anything out of a hat and it be legit and correct. But but all these topics are just kind of right there, ready to pull out. So I do have my awesome molecular model kit here, though. So I'm so glad. I'm so glad the Lewis structures helped. So, yeah, super cool. And even though you haven't done Lewis dot structures yet, I think you just knowing that it is really based on the periodic table, that will, as you learn more about the periodic table, it'll just give you things to watch out for that will hopefully help you in those realms. So very cool. I'm so glad. Yay. Okay. Let us, because we talked about ammonia, let's see. I wanted to do some structure stuff. Okay, so I've got these things called megamolecules. All right, and I really like this molecular model kit because it's small. So it's like this particular one, it's just this bag. Look at this. All the pieces, here, I'm gonna show you. All the pieces can fit in my hand, like just in one hand. Those are all the pieces that I need to create most molecules that I might want to create. Okay. And now they do sell these bigger kits. So I'll just show you this. Like this kind of site, like this is a box, and it's like there's quite a bit. I'll turn this over. Okay, so there's a lot more of the pieces. You can do a lot more with it. Okay, but in terms of if you just need a basic kit, then you can get this smaller one. Okay. Now, as a side note, I have a code that will get you 10% off if you want them, but we can worry about that later. Right now, I wanted to create the structure with you. All right. So, what we want are, we want to have a nitrogen, an atom here that represents the nitrogen. And then if we want to have 3 of those hydrogens. Okay, and then we'll bond them all together, and then we'll see what they look like. Okay. So I'm going to bring back that sheet that we started working on. This is so funny because I'm like, where's my sheet? Okay, let me put these down. There we go. Here's when we were working on the Lewis dot structure of ammonia. This was about an hour ago. And we decided, okay, here's the Lewis dot structure. Okay. Then you bring the molecular model kit into the picture. This is what is going to help you understand the 3-dimensional structure. All right, and this is all based on something called, I'll write it here, valence shell. Remember I was saying valence electrons. Those are the outermost electrons. Those are the relevant electrons in bonding. Valence shell, electron pair. Okay, electrons almost always appear in pairs when we're talking about bonding. And electrons are negatively charged, and so electrons will repel each other. And so that term actually comes in to this name, that those electron pairs repel each other. And this is the name of the theory we use to predict molecular shapes, molecular geometries. All right. So notice these letters. We've got our valence shell, electron pair, repulsion. Okay. This is then condensed down into VSEPR theory, which we usually say VSEPR. Okay. And VSEPR theory is saying that these electrons are going to repel each other as much as possible. So when we go back, we look at the Lewis dot structure, we identify the electron pairs that are around the central atom. So in this case, we say, all right, here's a pair, here's a pair, here's a pair, and here's a pair. We don't worry about whether they are a lone pair or in a bond. We don't even worry if it's a single bond versus a double bond versus a triple bond. We just say, okay, here's a blob of electrons, basically. And we see that they're all together. And here's another blob, okay, or electron cloud, they're sometimes called, okay? So the take home here is that around nitrogen, there are 4 separate electron clouds. And they are all going to repel each other. It's like we say repulsion. As much as they possibly can to get away from each other as much as they possibly can. And they do this for energetic reasons. The more that they repel each other means the further they move away from each other, which means they are then minimizing the repulsions, making overall the structure more stable. Dick Stortis says, they are clouds until you look at them and they suddenly turn into a particle. Yes, that is the basis for quantum mechanics, right? The wave-particle duality of matter, and especially with electrons. Yes, I love that. Okay, so what does that mean? Okay, well, when you have, like we see with the nitrogen here, when you have 4 electron clouds around a central atom, you get a shape that looks like this, okay? And this is always one of the possible shapes that will exist in any molecular model kit, okay? And check this out. This is what we call a tetrahedral shape, okay? That each of these, they're kind of sticks coming out, right? Okay. These are essentially where we're going to have a lone pair or a bond. So if it's a lone pair, you just imagine that the lone pair is hovering around this stick. And if it's a bond, then that's when we use these pieces. Okay, these are connecting, these are for connecting 2 atoms together. Okay, and then we imagine that the electrons are residing in this area that's between the 2 nuclei. Okay, so this round ball here, that's representing the nucleus and the core electrons of whatever atom that is. And in this case, it's the nitrogen. Okay. So once we acknowledge that there are 4 electron clouds and we choose that central atom that has 4 of these electron clouds around it in this tetrahedral shape, then we can begin constructing the rest of the molecule. So you do have to select the correct starting atom with those 4 electron clouds around it. Okay, and we did. We found it. We found that tetrahedral. So now we can put those 3 hydrogen atoms around it. So here's a bond, nitrogen, and then we need a hydrogen. The convention in many of these molecular model kits is that white is used for hydrogen. The convention is also that black is carbon. All right. Usually nitrogen is blue, but it doesn't really matter. With the main thing that's important is that you get the right number around here and in the right shape. So we don't need to worry about the color. I'm just telling you what the convention is. Okay. So we've only put one hydrogen around here. So then we can take another one of these bonds, put it on here, and we can then put another hydrogen. And then with the third, and because these are all symmetrical around the central atom, I'm arbitrarily choosing which location to put that bond on. And then there's the hydrogen. Okay. We have now officially finished constructing our ammonia molecule. And now let's inspect it. Let's take a look at this shape. And also, let's acknowledge what's in this location here. Right here, this is where there's that lone pair. This lone pair of electrons, there's no nucleus that's up here. It's just this cloud of electrons. Here, we've got a hydrogen nucleus. Here we have another hydrogen. Here we have another hydrogen nucleus. Here we have another. And there's our nitrogen nucleus. Okay. So where we have nuclei, those are dictating the overall shape of the molecule. The location of the lone pairs, those will absolutely affect the shape. All right, but we don't count them as being like one of the points of this is the skeleton of that structure. Okay, so when we look at this shape, we consider just where the nuclei are. So we see that nucleus there of this nitrogen, this hydrogen, this hydrogen, this hydrogen. If I set this down on the paper, notice how it's not lying flat. It's like a little pyramid. Here, let me, so you can have a side view a little bit better. I'm going to hold this piece of paper here, or this card, and then we'll put this up against this so you can see a side view. See how this is a pyramid, but it's not a four-sided pyramid like the pyramids in Egypt. This pyramid has 3 legs on it, right? Trigonal is the word we use for that. Trigonal. Tri for 3. So, the name of this shape is trigonal pyramid. All right? It's hard to see how this is a pyramid with this bird's eye view. Although, look, I can move my camera so you can see a little bit better. Let's see. You can see a little bit better how it's hovering above. Let's see that trigonal pyramid shape. Okay. I like that. Okay. Oh, cool. I like it. So, if we had to draw this is the thing, is we can build these shapes But a lot of times we want to depict them in 2 dimensions. We want to draw them out. And so the way that we can do that with our ammonia is that we can show the ammonia with the nitrogen atom there and one of the hydrogen atoms in the plane of the paper. So this would be kind of like this one if I, let's see, held it like this. So this hydrogen here is corresponding to this hydrogen here. Okay, but look at this one. This one's coming way out towards us. It's a lot bigger because it's closer to us, so it looks larger. All right, it's not actually bigger, it just looks bigger. But showing that it's bigger gives us the impression that it is closer to us and gives more of a 3-dimensional feeling. And so this is where we can use what's called wedge. And this wedge shows us, this hydrogen is bigger. We can even draw the hydrogen bigger if we want the H being a little bit bigger than that. So this gives a little bit of 3-dimensionality to this. And likewise, let's now consider, let's see. All right, so this hydrogen in the plane of the paper, this one bigger coming out towards us. Look at this one though, going way back behind, and it's smaller because it's further away. Okay, so the way we can do that, just like with the wedges, we can do this dashed technique to show that it's going back behind the plane of the paper. And again, you can draw that hydrogen being a little bit smaller to show that. Okay, so these are called dashes and wedges to show that 3-dimensionality. All right, and we can also show what the bond angle is. This helps give us an idea of what the shape is. So a tetrahedral shape, if this were perfectly tetrahedral, it would be 109.5 degrees. But we've got this lone pair here. And the lone pair is not stretched along the length of the bond, but instead it's only next to the nitrogen. So it actually kind of gets squished close to the nitrogen and ends up pushing these a little bit closer to each other. Okay, so it makes this bond angle a little bit less. So whenever you see a lone pair, then you know that the bond angle will be less than what it would be if this were a bond here. Okay, so there's a question. Are there cases where there's an extra electron not part of a pair? Yes. Yes, there is. And now they're fairly rare. And these are called radicals. Radicals when there's an unpaired electron. And there are a few examples. And let's see. I'll show one of them. And interestingly, they tend to happen on nitrogen more than any other. If we're looking at nonmetals and molecules, It's really common with nitrogen. Nitrogen just seems to be a little bit more stable, having only 7 electrons. So here's an example. And this has been shown, supported with instrumentation and data that show that there is an unpaired electron on the nitrogen. Okay, so this molecule here, the common name of this molecule is nitric oxide. This is not nitrous oxide that you get when you're at the dentist's office or laughing gas. But this is a really interesting molecule. Turns out, it wasn't known until the 1980s or 90s that this molecule plays a really important role in our physiology, and that it is related to constriction of our blood vessels. And also, if the concentrations of this are too high, it can actually kill the cell. So there are some people who are investigating how this molecule could be delivered in a therapy to kill cancer cells. So this is being investigated in cancer treatment and cancer research. So that's pretty cool. But to answer your question, it is known that there is an unpaired electron and it's on the nitrogen, and it's essentially breaking those rules that we learn about, that elements need to have their octet. Whereas here, how many electrons does this nitrogen have? So we can look at this and say, all right, here's a double bond. All right, so a double bond is a pair of electrons, a pair of electrons. So there's a total of 4. Here's another pair, so there's 6. And there's that single electron, that radical electron. So in this case, nitrogen has only 7. As a result, this nitrogen is fairly reactive. It's a little bit more reactive than it would be, like, say, in ammonia. Here it has its octet. 2, 4, 6, 8. So this nitrogen has its octet. This molecule is more stable than this nitric oxide. So some very, very interesting chemistry with it. So yeah, I love that question. I am all about these questions, so let me know if any more come to mind. Happy to answer them. All right. Let's create another molecule. Oh, you're welcome. I am always happy to work through problems. Okay. So let's see. There's so many different examples we could use. I think why don't we look at carbon dioxide and what the Lewis dot structure would be, as well as what the molecular shape would be. Okay. So, move my ammonia out of the way. All right. Let's look at this. carbon dioxide. And we'll do Lewis dot and the molecular structure. Okay. So the very first thing with our Lewis dot, we need to decide what is going to be the central atom. One trick, I would say, is that you always consider that it's probably going to be the first element that's listed. That's not 100% always true, but very often it is. Okay. The next thing you check for, along with like what we saw with ammonia, it's like, okay, we know that the hydrogens cannot be the central atom. So that's one thing to consider. But here we don't have hydrogen, so we don't have to worry about that. But what we can look at is which one of these is the least electronegative. And that will be the central atom. Okay. So, periodic table, bring that in. Here's our carbon. Here's our oxygen. The trend for electronegativity, it increases as you go across. So which one is more electronegative, carbon or oxygen? Which element is more electronegative, carbon or oxygen? I should try. Have I done this before? I should try doing a poll because I've never done one. Oh, is this gonna... Okay, I don't know. I'm gonna try it. Okay. Here, okay, I'm gonna try. Maybe I wanted prediction, but anyway. Or electronegative, carbon or oxygen. Okay. Let's see. Okay, we'll try this. Oh goodness. Did it work? I don't even know. Oh, okay. I just put up a poll. I don't know how it shows up to you, but I just put it up there. So, if you know how to answer a poll, please do. I've never done this. Oh my gosh. Which is more electronegative, carbon or oxygen? Okay, one person has answered. Yay. Thank you. And I only gave you 1 minute, so time's gonna run out. But if you do have time to get in there, you still have a little bit, and let me know what you think. This is anonymous, right? Okay. Which is more electronegative, carbon or oxygen? Okay, it is oxygen. Yay! All right, and one brave soul answered. Good job. It is oxygen. Yay, that was my first poll. Thank you. Thank you. All right, cool. So, oxygen is more electronegative. That means oxygen is going to be more stable on the outside of the molecule. So when we are then constructing carbon dioxide, we will put oxygen on the outside. So we know that there's one carbon, and we know that there are two oxygens. So we are going to flank the carbon by these two more electronegative oxygens. Okay? So this is our basic skeleton. This is our starting point. All right? Next thing we want to do is count up all of the electrons that exist for this molecule. So that means, and when I say add up all of the electrons, I mean the valence electrons. So we're going to look at oxygen and carbon. Carbon, there's only one, so we'll multiply that by just one. Oxygens, there are two, so each one will contribute however many valence electrons those have. All right, carbon. Here is carbon on the periodic table. It is in group 2. Okay, here's group 2. So now I'm going to try a prediction. And you are going to predict how many, I don't like this light here. Okay. You're going to predict how many valence electrons carbon has. Okay? This one might be tricky, but let's try it. Okay. So I'll get my keyboard and type this in. Prediction. Okay. All right. So start prediction. I want to do a new one. I hope this works. Okay. Okay. Does carbon have, or I know, how many, my question is how many valence electrons does carbon have? And then I'm going to give you two choices. And I'm going to give, do you want more than a minute? Do you want 2 minutes? Or is that too long? I'll give you 2 minutes. Okay, this is my first prediction ever. Okay, got it. All right, there is now a prediction happening. Okay. Okay, how does this work? Oh, and I guess you have to use 10 moles. Okay, that's not too bad. I think that's right. So we have this is so funny because I can't, here, I'm going to move my keyboard is kind of in the way. Okay, here's our periodic table, right? And we are predicting, oh, is it like gambling? Oh, Dick Stories, does somebody win the points? I can't remember how this works. Oh my gosh, there's like, oh nice. You have your periodic table pinned up on my desk bulletin board. I love it. Eileen, that's great. Yeah, the prediction is still happening. So the prediction is, I set it for 2 minutes to give people some time to think. So this is fun. Thank you all of you for doing this with me and for being here. And oh, the betting stage is finished. Okay. I think I have to do something now. Oh my goodness. What do I do? Where is it? Okay, maybe I'll I think I have to like tell them what the right answer is. If I can spell prediction. Okay. Yes. Okay. All right. Prediction result is 4. There are 4 valence electrons. So, what does that mean? Okay, I'll just close that up. All right, so how many people got it right? I don't know. We had a correct bet. Oh, I see. Everyone got it right. Well, that's kind of a win, right? Everybody bet correctly. Okay. Here's carbon. Carbon, I'm going to bring this closer. I want to hit this home. Okay. We got a bunch of, yes, improving self-esteem, improving confidence in chemistry. Confidence and chemistry both begin with C. Carbon begins with C. Does that mean I need to ask a harder question or a trickier question next time? Interesting. Okay. I also wanted to thank Toka Tutu Kirishima. Thank you. Thank you for following. That's awesome. Okay, so here's our carbon, and everyone correctly answered that carbon has 4 valence electrons. So just like we did with nitrogen, we went to period 2, 1, 2, 3, 4. These are our valence electrons. Now, the reason why I gave 6 as a potential answer is because carbon is element 6. And so there are a total of 6 electrons in carbon, right? But 2 of those are core electrons. They are not valence electrons. So, okay. So we've got, in terms of valence electrons, we have 1 carbon, and it's got those 4 electrons. Oxygen. Each oxygen has how many valence electrons? We're not going to do a prediction for this one. I will be doing another prediction shortly, though. Okay. So oxygen is 2 past carbon, right? So 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. Okay. So 1 times 4. Hey, I can do that in front of a bunch of people. 2 times 6 gives us 12 electrons. So that means there are a total of 16 electrons in the valence shell, or in other words, that are involved in the bonding and that affect the molecular structure of carbon dioxide. So this is what we can start doing, is that the rule of thumb is we can begin surrounding the more electronegative atoms with electrons until they're full, and then we follow up with adding any remaining electrons to the central atom. And then we got to double check, do they all have their octet? And if they don't, that's when we might have to move electrons around to create double bonds or triple bonds to give each atom their octet. Okay, so I just said a lot right there. So now we're going to go step by step through the process so you'll see it happen. Okay, so keeping in mind we've got to have a total of 16 electrons. And so far we've used up 4 of them. We've used up 4 of them, so that's 6, 8, 10, 12, 14, 16. Okay, in this method, we are giving the outermost, more electronegative atoms the electrons first. This method isn't going to immediately always give you the final answer, but it will bring you there faster, more often. Okay, but our next job is to check, do all the elements have their octets? So the molecule has all 16, so that's good. Oxygen has its octet, 2, 4, 6, 8. Both of them do. But does carbon? Okay, right now, carbon has 2, 4. This carbon is missing half of the electrons that it needs. But we can't just add in electrons into the molecule. We've got to work with the electrons that we have and move them around in order to give carbon its octet. But we can't take away electrons from the oxygens because they already have their octet. So this is a case where we begin sharing. We essentially move a pair of electrons from one of the oxygens over here so that the carbon can now share and gain a pair of electrons from this side. This oxygen is still sharing and has that pair, so it'll still have its octet. And same with this side. We will do it symmetrically. So if you have an eraser, then that works too. Otherwise, what I usually do is I just redraw it with those electron pairs moved. So see, we moved that pair and we moved that pair. Okay. So now let's check. This oxygen has 2, 4, 6, 8 electrons. It has its octet, yay. This oxygen is the same, 2, 4, 6, 8. Has its octet, yay. Okay. And then we check the carbon. 2, 4, 6, 8. Yes. Now the carbon also has its octet, and we are done. Okay. So here is, why don't I bring in my green pen? And we can say, yes. We have double checked that we've got all of those necessary electrons. Okay, so now let's look at the structure. Okay. In this case, carbon has only 2 of those electron clouds around it. Yes, this is a double bond, but these electrons are all in the same region. They are between the oxygen and the carbon. So this is considered one electron cloud in the case of figuring out the structure using valence shell electron pair repulsion theory. Okay, so using our VSEPR theory now. Chopper E13, hello. I know, I like them too. They're so nice. And I have 4 colors today, which are so handy. So we've got only 2 electron clouds around the carbon, in contrast to when we looked at ammonia and the nitrogen had 4 electron clouds around it. Okay, so that means we've got to look in our molecular model kit and find the nucleus that has 2 bonds coming out of it, or 2 things, 2 electron clouds. And I see it, so I'm digging in. My hand's in there. I'm gonna get it. There it is. Okay. So when an atom has 2 electron clouds around it, we think about how are those electron clouds going to get as far away from each other as they possibly can. And what they would do is they would essentially do what if there were 2 people in a room together and they were trying to get as far away from each other as possible. One would go in one corner over there and the other one would go in the other corner over there, right? They would be 180 degrees if this is the center of the room. Okay, they'd be at opposite ends. So that's the same thing with if you are going to choose. Yeah, they'd be at opposite ends. So if we have a central atom and then now we have 2 of these atoms that are on either side of it. The central atom, this is going to be the carbon. And if these oxygens are going to get as far away from each other as possible, they will end up being 180 degrees from each other. So and maybe this is a better analogy, that if you had a parent with 2 children and the parent is holding their hands, so the parent is holding one child's hand with the right hand and the other child's hand with their left hand. And imagine those kids are maybe angry with one another and they're trying to get as far away from each other as possible, but they're holding their parent's hand because they're in the grocery store. Okay, how are they going to do that? They're going to get on either side and maybe pulling their parent's arm a little bit, right? And trying to be as far away from each other as possible. So that is the case of carbon dioxide. that we have this kind of configuration. And now I can get the bonds. And I can get the oxygen atoms. I think I'm going to use purple. Or maybe... I feel like I have to just take whatever's closest. I wanted purple, but it's too far away. So, I'll take orange. Okay. So, here's my central carbon. And then I'll use this as a bond. And this is a bond. Now, keeping in mind, yes, these are double bonds, but we're really mostly concerned with the structure. And then I've selected a couple atoms that will represent the oxygen atoms. Okay. So, double bond, double bond. There's our oxygen, and there's our oxygen. Okay. There's our carbon dioxide right there. Okay. Chopper E13, I just caught what you said. I'm going to turn 360 degrees away from you. And then you're right back where you started. Exactly. All right, like if we spin this, it can go 360 degrees. Okay. All right, so what is the bond angle? Okay, we already said that, so, but let's just draw it up here. And bond angles always, we have the central atom in the center, and then we consider what's the angle between those two atoms that we're interested in. Like how far away are those from each other? And in this case, 180 degrees. Okay. So what is this one called? This is a nice, easy name because that's essentially a line. We call it linear, and that is considered the official name of that type of molecule, that shape of molecule. Okay. Whereas if you recall our ammonia, we figured out that structure, and I have it right here. Okay. This is a trigonal pyramid. All right, cool. So let's do another one. Okay. Let's do, hey, we're going to do a couple things. So Eily, you were saying that you're learning how to name. You're learning nomenclature, as it's called. You're learning how to name. So we're going to name this. And then we are going to do the Lewis dot structure of it. And then we are going to figure out the three-dimensional geometry of it. Okay. So, naming molecules. We've got our element here. What's S? I'm going to have all of you name this. So if someone can throw a name out there, or I will try another prediction. Yes, good job. You. Sulfur difluoride, exactly. Ooh, sulfur difluoride. Great. Okay. Now, Lewis dot structure. Which element will be in the center? Sulfur or fluorine? Which element will be in the center? S or F? Yes, good job, sulfur. Okay, so we'll put sulfur in the center, and then we are going to bond those two fluorines. Okay, so right now, this looks really similar to when we did carbon dioxide, right? We have an element in the center, and we have two elements flanking it. All right, so we're going to see how this goes, though. Okay. So let's count up the valence electrons. Sulfur. There's only one sulfur, so we'll have 1 times the number of valence electrons. And then we have our fluorine. There's 2 of those. And notice how I wrote fluorine here and not fluoride. I'm just writing fluorine as the element, so that's why I wrote it that way. Okay, let's look at number of valence electrons. Okay, I want to try this again. I want to do a prediction. I want to see how it turns out. And let's see. So let's do a prediction where we will ask I think I need to make my screen bigger. It's like I want more room. I wonder, okay. Okay, let's say, all right, I can't see, I know, I'll try this. Okay, all right, we're going to do a prediction. There's a prediction going, asking how many valence electrons sulfur has. So let's see. How many valence electrons does sulfur have? You have a few more seconds to answer in the prediction. Let's see how this one goes. Okay, what happened? Clearly, this is so good that I'm getting this practice prediction. Okay. All right, what happened? We have oh, I have to choose the outcome, right? Okay. All right, complete prediction. Yes. Okay, what happened? Prediction result is 6. Yes. Now. Oh, excellent. Oh, so Eily, you just won 30 moles. That's a lot of moles, actually. That's a lot of This is awesome. Eily, you just won. I'm so stoked for you. That's so cool. Good job. Super cool. So I think if someone wants to confirm, I believe that Eily was not the only person to answer correctly, but they answered the quickest, maybe? I'm not sure. But in any case, congratulations on winning. Good job. So, cool. I'm going to write that in there. Yeah. Very cool. All right. I love it. So, okay, you're like, okay, fine. That was fun, but let's keep working. Okay. Yes. All right. So our sulfur, we've got 6 of those valence electrons, which totally makes sense because we determined that oxygen has 6, right? Sulfur is right below oxygen on the periodic table. It has the same number of valence electrons. Yes, indeed. So we've got those 6 there. Okay. Fluorine. Oxygen has these 6, right? Fluorine is right next door. Fluorine's got 7. Yes. Oh, cool. Oh, I got a whole 1.8 times 10 to the 25th atoms. Yeah. That's a lot. Okay. So fluorine has 7 valence electrons. Okay. So now when we add these up, 6 of the electrons that are involved in bonding come from sulfur, that are 6, and 14 of the valence electrons that are involved in bonding come from those 2 fluorines. All right. So now when we add these up, whoops, it's not 1, this is a 2. We have a total of 20 electrons. So these are the total number of electrons that need to be accounted for in this structure. We've accounted for 4 of them. Each of these bonds is a single pair of electrons. So 2, 4, 6, 8, 10. Okay, so now we've accounted for 10 of them. Remember what I said, that we want to start out by surrounding the more electronegative atoms with those electrons first. So I'm going to skip over to the other fluorine and continue filling them out. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we've accounted for 16, but there are 20 All the fluorines are full. They both have their octet. Now we head over to the sulfur and we finish it out 18 and 20. Okay. So here are all 20 that are accounted for. Now we double check the octets. Fluorine has its octet. 2, 4, 6, 8. Yes. Sulfur, does it have its octet? 2, 4, 6, 8. Yes. Fluorine, octet. 2, 4, 6, 8. Yes. So this molecule, as it stands, is stable, and all those electrons are there. So we don't need to move anything. We don't need to double bond anything. We are good to go to move into the next step. Okay, so Eiley, you asked this great question. How do we know when to or when not to double bond? All right, let's go back to the carbon dioxide. Here, we had to double bond because that was the only way that the carbon could get its octet. So when we originally counted up all the electrons and we distributed all the electrons, carbon was left without enough electrons. So there was no other choice than to shift these electrons from oxygen in and create a double bond, because that allows oxygen to keep that pair of electrons, but to also share the pair of electrons, which then gives the carbon those electrons to count towards its octet. So even when atoms are sharing the electrons, they still get to count them towards the octet. So you will create a double bond when you're going through this process. You will create a double bond when it is necessary to make one of those atoms have its octet. So that'll be your clue. You'll get to a point where the central atom has 4 electrons or has 6 electrons, and you've got to do something. You've got to shift a pair around to give it its octet. And we can do another example of those so that you can see how that works for them. Okay, so another question. Jake Quarters, hi, good to see you. Thanks for jumping in here with a question. This is awesome. Okay, so the question is, so the bonds are 2, but counted for both, and then a single when counting. Let me make sure I understand the question. So let's see. Jake Quarters, just so I can answer correctly, is your question pertaining to CO2 or is it pertaining to SF2? I'm going to put CO2. And then I can be sure I read the question correctly later. Okay. Both. You figured it out with CO2. Okay, cool. Okay, cool. Yeah. Yeah, context is everything, right? Yeah. Okay, good. Yeah, so one, just let's look at the CO2 for a second here. When we're considering the octet, you essentially look at all those electrons, for a carbon. Anything that's around it counts for those electrons when we're like, oh, does it have its octet or does it not have its octet? So here, even though they're being shared, they count as being stabilizing forces for the carbon, and part of that, those 8. Sulfate, I did show sulfate earlier. But, yeah, which is different from these. And that reminds me, another example, helpful example, is drawing Lewis dot structures when it's an ion. So when it's an anion or cation, you have to do other things with the counting. You have to make up for the fact that there's either an electron lost or there's an electron gained. So that's something important. So I wanted to look at this, at the structure of this, and show you that around the sulfur, so we're done here in terms of the Lewis dot, but if we wanted to construct this molecule in 3 dimensions with a molecular model kit, we would then look at each of these electron clouds as separate entities. We would say, okay, here's one, here's one, here's one, and here's one around the sulfur. All right, so when doing VSEPR theory, we look at those electron clouds as separate entities, and we see that the sulfur has 4. So we would select the central atom that has 4 electron clouds around it that are separated as much as possible. And this is our tetrahedral type atom. And then we would add in the bonds to the fluorines. Okay, so fluorine is often yellow. We don't have to match the convention, but I do have 2 yellow atoms here. So we'll use those for the fluorine. Central atom here will be the sulfur. And then we need a couple bonds here. Okay, so here's our sulfur. Here's a bond to one of the fluorines. Okay, so we've created one of these bonds, just as shown here. And then we will create the other one. Okay, now you might be wondering, well, how do you choose which location to put the other bond to the fluorine? This is the thing. They are actually identical. Jake Quarters, I just saw your question. I'll speak to that in a moment. Okay, so let's create this bond. Because these are identical, it actually doesn't matter which one you choose. That's the beauty of that one, of this example. And here's our sulfur difluoride. So notice, even though on paper, when we're doing the Lewis dot, this looks like it's linear, it is not linear. And that is because of these lone pairs. So this is a lone pair here. This is a lone pair here. So there's a pair of electrons that's taking up space. And that is causing repulsion. Here's another lone pair taking up space, causing repulsion. So this structure ends up being bent. Okay, let me draw this. This is a bent structure where there's the sulfur and the fluorines are bent down away from those lone pairs. Notice how I drew these lone pairs on one side, fluorines down on this side, just as the molecular model kit predicts. So these model kits are so great to have They can help you visualize what's going on. And now, if we think about the bond angle, just like we did with our ammonia, which is perhaps our segue into Jake Quarter's question, but here we had 109.5, but it was less than 109.5 because of this lone pair pushing down extra. Well, the exact same thing happens here. Now we've got two lone pairs pushing down, distorting this angle that would normally be 109.5. Those lone pairs are pushing. So it's less than 109.5. Less than 109.5 degrees. Okay? Now you might be saying, why do you just keep saying less than 109.5? Well, off the top of my head, I don't know what it is exactly. Okay? I'm sure somebody does. It's been measured, no doubt, and that is known. But in terms of learning about, oh, gotcha. No, that's okay. We just looked at the structure of it. So, yeah. We know that it's less than 109.5. And for learning molecular structure, that is actually good enough. If you need to go deep into a particular molecule, then that's where you can dive in and search for the research paper that discovered what is the actual angle. They're very well known for especially something like ammonia that's so common. Okay. So let me look at this question again. Okay. So Jake Quarters is saying, I work in renewable energy. Awesome. I'm exploring green hydrogen and derivative fuels. I love it. My PhD was actually in investigating catalysts, model catalysts for the formation of carbon-carbon bonds in man-made fuels, in renewable fuels. I've since moved away from that research, but I'm still very interested in it. Okay. Currently I have engineers in town from Black and Veatch in town. Oh, that's so cool. They're teaching about ammonia. Is there any ammonia? Yeah, so I see what you were saying is going back, because we used ammonia as our very first example. And for those of you that have joined since then, and just considering ammonia as this example, looking at how you do a Lewis dot structure and how to choose the central atom. And in this case, we saw that nitrogen had to be the central atom because hydrogens can never be a central atom, since they can only have 2 electrons and create only one bond. So then we went through the Lewis dot and added up the valence electrons. We saw there were 8. So then that allowed us to create this Lewis dot and then create the 3-dimensional structure. We decided that it could not have a structure that was linear like this with hydrogens in a row because, again, hydrogens can only have one bond, so that would be impossible. Here's another way to show that Lewis dot structure. And the 3-dimensional structure is this trigonal pyramid. Okay. So, yeah. And ammonia shows up in so many places, you know. It's such a quintessential example when you are talking about the Haber process, Haber-Bosch. So this particular chemical reaction right here makes billions and billions of dollars every year because of what ammonia can be used for. There's so many uses of ammonia. You know, in everyday life, we just think about cleaners, and that's like window cleaner. You know, that's just one of so many things. There are so many drugs that have nitrogen and amine groups as part of them. Fertilizers, huge, huge, huge. Fertilizers that have ammonia. Plants need ammonia, right? And so if you just combine fertilizers and drugs, those alone are probably most of those billions of dollars. But there are also other applications, other materials, and I'm just thinking of peptides and biological molecules like that. Whoops. That would use ammonia as well. So many different applications. All right, so part of the trick here is nitrogen taking over fertilizer industry. Yeah. Haber-Bosch. Yeah. Yep. I see you put haven't Bosch. Gotcha. Yeah. Yeah, I have a feeling autocorrect maybe isn't familiar with Haber, but that's okay. Yeah, being able, I mean, you think about it and what's needed for food and growing food and how important ammonia-based fertilizers are, and that is enormously important in this world. So, isn't that funny? So earlier in the stream, we had someone redeem 500 channel points for me to bring Neil the chemistry corgi into the stream. So, by the way, if anyone wants to see the corgi, he's right over there. Oh my gosh, I think he's actually in my window. You could almost see him. Anyway, and so when I brought Neil in, right? It was you, right? It was you that you were like, oh, he's so cute in all caps. And then the Nightbot freaked out and like deleted the comments, and it was so funny. Jake Quarters, nicely done. Redeeming Neil the chemistry corgi joins the stream for 500 moles. All right, it is time. Neil. Let's see. All right, I'm going to use this cam here. Okay, let's zoom in. Neil. Okay, as you could guess, sorry. Hi. He's getting closer and closer because of this. Because of this. Hi. Is that good? It was so yummy. There he is. Hi, Neil. I need to teach Neil tricks. He is so fluffy. He's very fluffy. You should see his fluffy corgi butt. You can't really see it, but he is super fluffy. And tomorrow there he goes. Tomorrow he's going to the groomers, because he's shedding, and so he has all this like fur. Yeah. Where's your fur? Oh, there's your snout. Yeah, see, look at this like, he has all this fur, this fluffy fur. Yeah. Whoops. Hey, Neil. What's up? Hi. People are so happy to see you. All right. There's Neil. Neil, the chemistry corgi. So, Neil is 2 years old, but sorry, my hand is in the way. Okay. Neil is 2 years old, but he is going to turn 3 next month. And this is terrible. I forgot his birthday. I think it's October 12th, but I'll double check, and maybe we'll have a little Neil birthday party or something. I don't know. I'll have to do something. And he will turn 3 years old. So, yes, he is very sweet. Sweet and fluffy, and he's super mellow. So I very, very rarely hear him bark, actually. He only barks if he's still young. He usually only barks if someone rings the doorbell or knocks. That's about it. Oh, is he a Scorpio? No, he's a Libra, right? October 12th. Yeah. All right, cool. So there's Neil. Where was I? Oh, I think I was, I was just talking about the Haber Bosch. Right. Yep. Scorpio starts October 22nd, right around there. Right? No, October. Yeah, right around there. October 23rd or so. Yeah. And the main reason why I know this is 3 people in my family are Libras, and they are all October 1st and October 18th and October 22nd, which is on the cusp. So, yes. All right, cool. So, what other questions should I keep talking about Haber Bosch process, or should we do more molecular model kits, or what would be helpful? Yeah. And speaking of this molecular model kit, I do have, if any of you are interested, let me see, where is it? Okay, I'm going to copy this. Oh, yeah, I'd be happy to draw an ion. Totally. Okay. I'm also going to, for 10% off mega, I'm sorry. I like having this pen's much better. Okay. Okay. So if you are interested in these cool little molecular models that I've been using, I have an affiliate link. So that means if you buy them, then you get 10% off, and they give me 10% of the sale. So it's only a couple bucks, but hey, it helps. And they have a lot of different ones. So for example, this is the one that I've been using that's just like a small one, and you just get a few. So this one is probably pretty inexpensive. But then they also, if you're like, ooh, no, I'm a chemist and I want to get more, then you can get the advanced one that has a lot more of these, like pretty much everything that you'd ever need. So I really like them. There's a lot of molecular model kits out there, but some of them are kind of clunky, and some of them, I don't know, I feel like they break easy and other things. So that's why I like these ones. Okay, let's draw an ion. Oh, okay, yeah. So I'm going to do a couple things. Thank you for the request. It's awesome. I'm going to move my camera a little bit. Okay. So, because I had this up here, I'm going to say a couple more things about this. And then I want to draw an ion for you. Okay. So this particular process, this is exothermic. Okay. So exothermic. All right. So what does this mean? All right. So therm, the root here, means heat, right? And exo means out. And so what that is saying is that this releases heat. All right. So that's something that you want to keep in mind. I'm going to close the box around the heat here. When you're thinking about equilibrium, and that you can actually shift an equilibrium by either putting in more reactants, and this is called Le Chatelier's principle, that if you add more ammonia, this is ammonia. If you add more nitrogen, N2, you shift the equilibrium to the right, and it makes more ammonia. If you add more hydrogen, it shifts the equilibrium to products. Okay. So that's pretty intuitive. Adding more reactants would make more products. Okay. But there's another aspect to this, and that would be if you were to remove either a reactant or a product. So if you were to remove nitrogen from this equilibrium, it would actually shift the equilibrium back towards reactants to make up for the nitrogen that you removed. But the same goes with the ammonia. So if you have a reaction chamber where you are creating or synthesizing ammonia, if you are continuously removing the ammonia from it, it will shift the equilibrium towards the products, which will help you create even more products. So it behooves you to, in any synthesis, when possible, if you can remove more and more of the products as you are synthesizing that product, it allows the equilibrium to continually shift, making more products. Okay. Another thing that you can work with is by recognizing that it releases heat. And I can actually look that up and find out the amount that is. But if this releases heat, you can also work with the temperatures. So typically, this particular reaction is done at higher temperatures, higher meaning higher than room temperature. So it's pretty warm. It's like, 700 degrees Celsius maybe. Don't quote me on that, but typically done at higher temperatures. Now, this is the thing, is that chemical reactions happen faster at higher temperatures. And so when you're heating it up, so that usually comes from a typical heating source. So just like a home or a building has a furnace, then a reaction vessel, and so I'm envisioning in my mind like a big chemical industrial plant that has a big vat of ammonia. And so they're adding heat through a typical kind of big furnace sort of way. Okay. If you were, 900 degrees Celsius. Yeah. Okay. Oh, so I wasn't off too far when I said 700. That's good. Yeah. Okay. Now, when you said, where does the heat come from? If you were talking about this heat, that when I wrote heat is released, that heat comes from the bonds being formed in the ammonia. Okay. So what that means is that there's bond breaking of the reactants and there's bond formation of the products. And if you are creating more bonds that are more stable for the products, then heat will be released. If you need to break more bonds and put more energy into breaking the bonds, then it will be endothermic and you'll have to add heat in. So nitrogen is the strongest covalent bond. So you do have to put in a lot of heat, but look at over here. Not only are you creating 3 bonds, but you're also creating 2 molecules. So you're creating a total of 6 bonds over on this side. And so that's why this ends up being more stable in terms of bond energy. And so that leftover heat is then released. So, yeah. Yep. Cool. Okay. We're going to switch gears because I need to answer. You asked, can we draw an ion? Because yes, ions have another little hitch to them. I already drew on that side. Okay, so tabla rasa. Okay, we've got a clean sheet of paper. I'm going to move up my camera a little bit. All right. And let's draw okay. Lewis dot, why did that happen? Okay. Lewis dot structure of, I am going to keep within our theme of ammonia, and let's do ammonium. Okay, so they're related, but we get to look a little bit at the cation equivalent of ammonia. All right, so ammonium is NH4 plus. Okay, so there is an extra hydrogen here, and overall it has a positive charge. Okay, so Eileen, thank you. Oh, an anonymous gifter gave Eileen a tier 1 subscription. That's so cool. Thank you, anonymous gifter. How awesome is that? Yay. Love it. Okay, cool. Yeah, thank you to everyone who has subscribed, who has followed, everything. That's so great. All right, cool. So let's follow. Oh, Eileen, you just used the Neil the chemistry corgi emotes that you get with a subscription. That's so cool. I love it. Okay. So with ammonium, all right, let's look at this. We're going to do a couple things. We're going to draw out the skeleton structure, and then we will count up all the electrons. All right. So we will start with choosing the central atom. Okay. Following the rule that hydrogen can never be a central atom because it can only ever have one bond, that leaves only one option. It must be the nitrogen. And we see that there are 4 hydrogens that are bonded to the nitrogen. Okay, so let's bond those 4 hydrogens around the nitrogen. Okay. Next, we need to acknowledge that this is a cation. It is not a neutral molecule. If we left it drawn as it is right here, right now, this implies it's neutral. But ammonium is a cation. It is +1 charged. So the way we do this, the convention is we draw brackets and then we have a plus charge. Okay. Now, let's move forward and let's count up all of the electrons. So for nitrogen, we have 1 times. We need to find the valence electrons. Number of valence electrons for nitrogen. Okay. Here's our nitrogen. Right? It's in period 2. 1, 2, 3, 4, 5. All right, 5 valence electrons. All right, and then we've got these 4 hydrogens. 4, and those each contribute 1 electron each. All right. So if we count these up, we would get 9 electrons. Okay? But look at this. Nitrogen has 2, 4, 6, 8 electrons around it. There's nowhere else to put that 9th electron. Okay? Ammonium cannot have 9. Well, then that makes sense that it is positively charged. Positively charged means that it has 1 fewer electrons. Electrons are negatively charged. So if we remove one of these electrons, -1 electron, this is due to the +1 charge. That's how we get, I'll move this over. That's how we get those 8. So when you have an ion that is positively charged, you've got to take away that same number of electrons. When you do that, then you will end up with the final count of how many electrons there truly are in that ion, in the bonding, the valence shell of that ion. Okay? So with our ammonium, we end up with 8, and there are the 8, and we're done. We don't need to change everything else. Hey, Duckburg. Nice to see you. Thank you for stopping in. And let us know if you have a chemistry question or if you're just hanging out. Okay, this is an example of a cation, okay? Now, in case you're curious, yes, we'll do an anion. Let's do an anion next. But I did want to say, in case you're curious what the structure of ammonium looks like, now we have 4 bonds, right? And so we're going to use that same central atom that we've used a couple times now, that has 4 electron clouds around it, but now all 4 of them will be bonded to hydrogens. So the structure of ammonia is not this flat, square looking thing. In 3 dimensions, this is a tetrahedral structure. And now is perfectly 109.5 degrees for the bond angles. Okay, there's no lone pairs. And this is perfectly symmetrical. If you were to actually create a triangle and put it on this face, this would be a 4-sided DND. Okay, let's see. J quarters, IRL, you can't just take away an electron though. No, that electron does not exist in this ion. So that electron is gone, and electrons are added and taken away all the time in what are called redox reactions. So oxidation reduction reactions are where an electron is transferred from one entity to another. So there is no problem with taking away electrons. That does happen. It's not an issue. You can't just randomly take them away. There needs to be a reason for it. In this case, this structure only exists with 8 electrons around the nitrogen. It will not hold a 9th electron. So this is how ammonia exists. Okay, so let's look at an anion. Because we talked about sulfate before briefly, yeah. In fact, the Haber process, Haber-Bosch process, is a redox reaction. So there are electrons getting shifted with both the nitrogen and the hydrogen. And yeah, if you might be watching the chat, but did want to just remind everyone that if you're interested in the Discord channel, you can join with the link that is there. And thank you to everyone who's followed and subscribed to this channel. I so much appreciate it. Okay, let's check out sulfate here. All right, so we can start out with our usual process of let's take our sulfur and let's surround it by those 4 oxygens as a starting point. Okay, but then we would want to know, like, all right, how many electrons do we have? And we have a sulfate that's -2. What do we do about that? Okay, so let's look at sulfur. And hey, we did a prediction earlier. How many valence electrons does sulfur have? And we decided it was 6. Okay, so that contributes 6. And then in terms of the oxygens, there are 4 of them. And oxygen is also 6 valence electrons. So 4 times 6, we get 24. All right, so now when we add these up, we have a total of 30. Okay. But now we've got an anion. Okay. So when you have an anion, once again, you have to bracket the structure and you have to acknowledge what the charge is. Okay, so we put a -2 there. And then in terms of adding up the electrons, there are 2 additional electrons, right? This is 2 minus -2 overall. So that means there are 2 additional, and this is due to the -2 charge. Okay, so I know it seems funny and maybe not intuitive that when there's a positive charge, you subtract an electron, and when there's a negative charge, you are adding 2 electrons here. Okay, but that is just because electrons are negatively charged. So removing a negative charge is the same as adding a positive charge, right? Or adding a negative charge is the same as ending up with a -2 charge. So it's a little bit weird, but once you think through and just remember this idea of electrons being negatively charged, it totally works out. No problem at all. So Nanaki 115, very cool. It's so good to have you here. Thank you for lurking. I love that word lurk. It's just so, I don't know what it is. It's like, I don't know. I like it. Okay. So this is where we get the correct number of valence electrons to work with. And from here on out, you just do everything you would normally do for a Lewis dot structure. So this step here that we saw with the cation and with the anion, this is the extra step that you do for anions and cations, ions in general. Okay, so let's finish off our sulfate. We have 32 electrons to account for. So far we've accounted for 2, 4, 6, 8 of them. So then we could say 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There they are. Okay. And now we can double check and make sure that all of these atoms have their octets. Okay. Sulfur 2, 4, 6, 8. Yes. Oxygen 2, 4, 6, 8. Yes. 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 Everyone's got their octet, stable as can be, and we are done. Okay. Side note. There is something called formal charge. This is beyond the scope of this live stream right now. But I am going to say this for now. Okay? We can talk about formal charge at another time, and it changes a little bit of this, but this is, if you're considering, I I gesticulate. Do you know that word? Like, I talk with my hands a lot and I bump everything. I bump my mic, I bump my camera, I kind of just bump everything. Okay. Anyway, for the purposes of any beginning chemistry student, before you have learned about formal charges, this Lewis dot structure follows all of the basic rules of Lewis dot structures and octets. So, so this is fine. Once you learn about formal charge, then you can think about this in a slightly more sophisticated manner. But for now, this is fine. Awesome. Okay, so you're very welcome, Iliu. My pleasure. I'm glad it was helpful. Okay, so J quarters. Sorry. Did we know? Did you mean S? Sulfur? You said A was in the middle, but I'm thinking maybe because A is next to S on the keyboard. Did you mean S? I will point out, if you are wondering about how to know that S is in the middle, a few things about that. So first off, the central atom, okay, sulfur, yep, sulfur in the middle. Okay, so let's take a little, I don't know, this is related, okay? So central atom, okay, is going to be the least electronegative, negative. So that's something that we've talked about. We will never see hydrogen because hydrogen can only have one bond. Okay. The reason why least electronegative in the center is because it's more stable that way. If the least electronegative atom is in the center, by default, that means the more electronegative atoms are on the outside. And if that is true, what that does, like in the case of oxygen is very electronegative, is that allows oxygen to have more electron density around it. So this oxygen atom, see, it has these lone pairs. So it essentially, if we want to anthropomorphize, sorry, I totally botched that word. But if we want to, I need to get that word down, but to use less scientific terminology, we could say the oxygens are hogging the electron density. And so because oxygen's more electronegative, it is more stable with more electrons around it. Sulfur, on the other hand, is less electronegative. It is sharing all of the electron pairs. And because it's less electronegative, it is stable doing so. So by putting the more electronegative atoms on the outside, you are inherently making a more stable structure. Okay? Another rule of thumb here is that molecules and these are especially without carbon. Be compact. Okay, as opposed to, okay, I got that covered up. Okay. carbon, on the other hand, can form long chains. So you can be less concerned about making a compact molecule when you have carbon as the central atom. So notice here's some examples of what I mean by making a molecule compact. Let's look at sulfate. Okay, we just did sulfate, right? And we had these oxygens surrounding the sulfur, okay? And that was, and I'm just gonna imply those electrons are there. Okay, it looks like this, not like this. Okay, this would be more of a long chain structure. This is much less stable. Okay, the reason why this is much less stable is, again, these oxygen atoms are quite electronegative, and so this oxygen here in this particular configuration, this oxygen would be sharing electrons on both sides, and here is an oxygen-oxygen bond. These are pretty unstable bonds. In fact, many molecules that have oxygen-oxygen bonds are explosive. Okay, so again, these are both electronegative atoms. They're the same electronegative atom, and so they are competing for drawing electron density towards themselves. So when each of these oxygen atoms draws electron density towards itself, that is inherently weakening the bond between them. Okay, so the net result is that if you make it more compact with sulfur in the center, surrounded completely by the oxygens that are separated from each other, you will have a more stable structure, and this is the one that will exist. Okay, on the other hand, if we are looking at carbon-based compounds, and this is what makes carbon such a fascinating element and is the origin of a whole field of chemistry called organic chemistry, is the fact that carbon can and does readily form chains. Okay, so it's no problem at all for us to have a carbon chain that looks like this. Okay, and maybe it's surrounded by hydrogens to have its octet. Whoops, I just drew an oxygen. No problem. Let's just make that I need to move this so I can shift up my, Okay, I want you to see this whole thing. Okay, so I'm just making up a fairly random organic molecule. This happens to be pentane, based on the fact that there are 5 carbons. And it's pentanol because this is an alcohol group. So, no problem. This is very stable. Carbon has no problem in forming these chains. Okay. So, in terms of selecting your central atom, if you follow these rules, then you will pretty much always be correct. And this is mostly just to say, hey, don't worry, if you have a bunch of carbons, that's fine. And usually we'll say, hey, which carbon are you interested in considering, as the central atom? Oh, this one here, or no, this one here, and so you tend to focus on Sure. Yeah, I'll draw butane, isobutane. So, yeah, organic chemistry is awesome. Personally, I did not get my PhD in organic chemistry. My specialty is metals, but I do love and appreciate organic chemistry. I loved that course when I took it. All right. So, butane has several isomers, okay? So we have something called N-butane, which is essentially just the long chain form. And butane, the prefix but, implies that there are 4 carbons. Okay? And so if we're drawing it in the full Lewis dot structure, we would draw it out this way. Okay? But that gets old, doesn't it? When you're drawing it out. So instead, if you want to use a pentane. Oh no, that's okay. No worries. If you want to use line angle drawings are fabulous, okay? But it does at first, it might be a little bit confusing. But here's the deal. Anytime you see the end of a line, it implies there's a carbon there. Anytime you see a bend in the line, it implies that there's a carbon there. Okay? So, this structure here, carbon, 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 carbon. There are 4 carbons here. If you do not see any hydrogens, it is implied that the hydrogens are there and that there are enough hydrogens to fill the octet. So it is assumed that everything is stable. So this carbon would have 3 hydrogens, just like we see when we drew it all out explicitly. This carbon here, it is implied that there are 2 hydrogens there. Same with this one, 2 hydrogens, and this one has 3. Okay. Eileen, you are so welcome. You're so welcome. And good night to you, and sleep well, sweet dreams. And yeah, it is probably late where you are. It's pretty late where I am. I mean, it's late for me because I haven't had dinner yet, and it's already 8:20 at night, and I'm getting hungry. So I will be stopping the stream soon, but this is awesome. I think this is the longest I've streamed before. It's over 3 hours, so that's pretty cool. Okay, so this is just N-butane. All right, but you also wanted to see, yeah, you're 11:20 at night. I totally get it. Bye, Eileen. So great to have you. Have a good night. Cool. Okay, so isobutane. This is an isomer of N-butane. Okay. So an isomer has the same molecular formula. Let's look at the molecular formula of this. It is 4 of those carbons, right? And then we have 6, 8, 10 hydrogens. Okay, isobutane looks like this. We've got 1, 2, 3, 4 carbons. Okay, so that's still true. And now let's count the hydrogens. This carbon here, it's only bonded to 1 other carbon, so it has to have 3. This carbon here, same thing. It's got to have 3. This carbon here, it's got to have 3 hydrogens. Okay, so 3, 6, 9 hydrogens are accounted for from those outside carbons. But what about this central carbon? It is bonded to 3 carbons. That means that there must be a hydrogen that's bonded to it in order for it to have its octet. So this also has 10 hydrogens. So these two structures of butane, these are isomers of each other, structural isomers, but they have the same formula as isomers do. But here's the difference in the structures themselves. Okay. All right, I am going to get myself some dinner, but thank you everyone who hung out here. I know some of you were here part of the time, some of you were here all the time. I did want to make sure that all of you know about my sponsor, Study Soup, an awesome company that supports college students in so many ways. Me doing this stream by Jake Quarters, yeah, take care. That, like me, I'm supporting students in chemistry, and so does Study Soup. They also support students in many other fields, many other topics, many other courses. So if you go to studysoup.com, you can find out more about them. There's also a link to a Discord channel if you're interested in that. And I do invite you to follow if you haven't already. Thank you so much for all of you who have. And hey, I'm going to put this in here. I have a YouTube channel. It is called ASMR Chemistry. And I have a ton of videos. And in fact, Jake Quarters, I don't know if you're still here, but I do talk about, there's at least one that's organic chemistry of different fuels. So, and there's a lot of other ones as well. So there's a lot of different topics are covered in that YouTube channel, and I just keep adding to it. So, all right. Well, thank you everyone for being here with me. This was really fun. I wonder if Neil's nearby. Oh, Neil's okay. I know no one has redeemed the points, but I'm just going to show Neil really quick because you can kind of see his fluffiness. Bye, Neil. Oh, he's going to go back to sleep. Aw. He's napping. All right, everyone. Have a good night. Have a good morning, wherever you are. Thank you for joining me. And I will be back in 2 days. So at 5 p.m. Pacific time, I will be doing a co-stream on Thursday with Victorion. I will be doing, okay, I'll put it in the chat. Thursday, 5 p.m. Pacific time. Co-stream with Victorion. And we are going to be we're going to be doing some gaming. I think we're going to be doing what's it called? Stardew Valley, which I did for the first time in the last stream. So if you want to join for that, I am of course always open to chemistry questions at any time. So even if there is any kind of gaming going on or anything else, this channel prioritizes the chemistry questions. So always feel free to hop in and hang out, maybe even just if you're studying something else and this is good background for you, feel free to join. So you are always welcome. And I will see you all next time. So take care and bye for now.